Welcome back to The Explainer. Today, we're taking an exclusive, behind-the-scenes factory tour of the Roman Space Telescope's Grism-Prism Data Processing System, or GDPS for short. So slated to launch by May 2027, the Nancy Grace Roman Space Telescope is going to map the universe thousands of times faster than Hubble. We're talking about capturing billions of galaxies to really unravel the secrets of dark energy and dark matter. But as you can imagine, managing that absolute torrential downpour of information requires a masterpiece of software. If you've ever wondered how astronomers turn just a chaotic jumble of raw detector data into incredibly clean, precise measurements of the cosmos, well, you're in the exact right place. Let's get right to it. To really understand the challenge here, imagine you're at a massive, booming cocktail party, right? Everyone's talking at once, the music is blaring, and you were trying to listen to just one single quiet conversation all the way across the crowded room. That is exactly what observing with the Roman Space Telescope can feel like. The big question is, how on earth do you isolate the light from one specific star or one incredibly faint, distant galaxy in a sky that is just bursting with billions of overlapping light sources?
The main culprit behind this cosmic cocktail party is a technique called slitless spectroscopy. Now, traditional telescopes often use these narrow, physical slits to block out background noise and isolate the light from a single object. But Roman, it doesn't do that. Its Wide Field Instrument, or WFI, captures all the light sources in its massive panoramic field of view simultaneously. And to do this, it uses a piece of hardware called a grism. Basically, a grism is a grating and a prism combined, and it takes the light from an object and spreads it out into a beautiful rainbow fingerprint, which reveals its chemical makeup and speed. To put the scale into perspective, the WFI will capture nearly 100,000 spectroscopic sources per square degree. That's absolutely incredible for gathering massive amounts of scientific data quickly, but it absolutely guarantees that their expanded spectral footprints are going to massively overlap.
Okay, let's dive into this. On our tour today, we're going to start with the slitless universe problem, then introduce the GDPS pipeline itself. From there, we'll untangle the spectra with G2DP, extract the science with G1DP, and finally look at how you can actually simulate the Roman sky right now. Section 1, the slitless universe problem. Stop number 1 on our tour brings us face-to-face with the main villain of our story as we trace a single photon of light. And that villain is cross-contamination. See, when the telescope's grism disperses the light of a typical galaxy, that light gets completely smeared across 90 arcseconds of the sky. I mean, it covers more than 4,000 pixels. With the sheer density of sources Roman will capture, these stretched-out spectral images inevitably just crash right into each other. It becomes this massive, overlapping traffic jam of cosmic data, where the light of one galaxy bleeds completely into the light of its neighbor. But our secret weapon against that cosmic traffic jam is actually kind of elegant. Before we analyze the dispersed, smeared light, we capture a direct, undispersed image of the exact same patch of sky. This direct image essentially acts as a rough map. What's really interesting here is that by pinpointing exactly where the stars and galaxies originate in that direct image, we can start to figure out whose light is spilling into whose space within those dispersed overlapping footprints. Section 2. Introducing the GDPS. So who actually does all this untangling? Well, that brings us to the hero of our story, the Grism-Prism Data Processing System, or GDPS, designed by the brilliant folks at the Science Support Center at IPAC. Welcome to the master control room of the GDPS. Basic calibrated WFI spectroscopic data, what we call level 2 data, enters the science data pipeline right here. Conceptually, level 2 means the raw signals from the spacecraft have been converted into physical units of light, but they are still a totally jumbled mess of overlapping spectra. The GDPS then systematically processes it, calibrates it, and evaluates it, eventually churning out highly refined level 4 science products. These final catalogs are then delivered straight to the Roman archive for astronomers worldwide to dive into. Section 3, G2DP, Untangling the Spectra. Let's lift the hood on the first major processing engine inside this system, the Grism-Prism 2D pipeline, or G2DP. This is really where the heavy lifting of untangling the messy two-dimensional data happens. G2DP operates in a series of really critical steps. First, a vital module called chord mapping acts as our surveyor. It takes those direct image coordinates we mentioned earlier and converts them into bounding boxes right on the dispersed spectral images. Then, a flat field module applies corrections for small-scale background variations, like zodiacal light. And if you're wondering what that is, it's essentially faint sunlight reflecting off interplanetary dust right here in our own solar system. Finally, the data heads into decontamination, which is honestly where the real magic takes place. So the absolutely crucial point is this. The fundamental technical hurdle of slitless spectroscopy, which is spectral decontamination, is solved by leaning entirely on those direct image maps. You simply cannot clean up the overlapping background light without first knowing exactly where every single background object is located in the sky. Here's how that decontamination actually plays out in the pipeline. It acts almost exactly like high-end noise-canceling headphones. First, a module called Contam-Identify locates all the overlapping background sources that are invading our target space. Then, it models the contaminating spectra of those neighboring sources, cleverly using all available orientation roles of the spacecraft. Because Roman observes the exact same patch of sky from slightly different angles as it orbits, we get a really complete 3D-like picture of what is overlapping what. Finally, the pipeline mathematically subtracts that modeled noise, and what's left behind? A beautifully clean, isolated, one-dimensional spectrum of our target galaxy.
Section 4. G1DP, Extracting the Science. With our data now cleaned and extracted into a 1D format, we transition to the Grism-Prism 1D pipeline, or G1DP. This is the engine where those clean signals are translated into actual, measurable scientific parameters. Those freshly cleaned 1D calibrated spectra are now fed directly into the G1D engine, but they don't go in alone. The pipeline also ingests massive reference input files alongside them, things like specific emission line catalogs and spectral templates. You can think of these spectral templates as a kind of cosmic mugshot database of known galaxy types, quasars, and stars, all ready to be matched against our incoming signals. And this brilliantly illustrates how the G1DP pipeline acts essentially as a cosmic detective. It takes our clean spectrum and runs an advanced mathematical comparison, a noise-weighted fit, against that huge range of templates to find the perfect match. It analyzes the specific patterns of light being absorbed or emitted by the object to calculate a highly reliable redshift measurement. This redshift tells us exactly how fast the object is moving away from us due to the expansion of the universe. It then outputs a definitive list of the best candidate redshifts and their uncertainties directly into the final astronomical catalog. Section 5. Simulating the Roman sky. Now here's a really exciting part of the journey. You don't actually have to wait for the Roman Space Telescope to launch to start engaging with this data. The scientific community is already test driving this exact system right now. That's right, anyone can practice feeding data into this pipeline today, using tools like Roman iSim, which simulates highly realistic WAFI data, and the massive Open Universe 2024 datasets. You can access your own simulated, messy universe to untangle. And best of all, you don't even have to deal with the headache of installing these complex software packages locally. They're available in a pre-configured, cloud-based collaborative environment called the Roman Research Nexus. This makes petabytes of data, literally the equivalent of thousands of standard hard drives, accessible right from your browser without downloading a single thing. Just a quick clarification for when you do jump into these simulations, you're going to encounter a few different data processing stages. Level 1 data contains the raw, uncalibrated detector read ramps. That's literally watching the electrical charge accumulate on the detector's pixels over time, kind of like watching a bucket fill with rain. Level 2, on the other hand, contains the calibrated images where those accumulation slopes have actually been calculated into standard units of light. It's this calibrated Level 2 data that gets fed directly into our hero, the GDPS pipeline, to kick off the whole extraction process we just discussed. From messy, overlapping signals spanning thousands of pixels to precise, noise-canceled redshift measurements, the GDPS is just an absolute marvel of modern data processing. With the Roman Research Nexus waiting for you to test these simulated datasets and pipelines today, it really leaves us with one inspiring thought. With the software perfectly tuned and ready to untangle the universe, what hidden cosmic truths will you uncover in Cycle 1? Thanks so much for joining me on this explainer, and I absolutely cannot wait to see what you discover out there.